All right, well, there was a lot of derivation, but let's do a simple example just to kind of give some context to this. Actually, we can also use this to help visualize a little bit more stress distributions, okay? Uh, so this is actually problem 5.3 text. Okay? So this is actually 5.3 of Hibbeler. And here we have a shaft. Its outer radius is 75 millimeters. There's a torque applied at this point, and torque applied at the end. All right? It really doesn't give you a length. In fact, for these, it doesn't matter. Although it's kind of weird. It gives you length, but you really don't need them for these problems. Um, and it asks you to find the shear stresses at point A and point B. So point B is in between these two torques, and it's at the outer surface, 75 millimeters. Point A is between the fixed end C and this 10 kilonewton meter torque. And it's not on the outer surface. It's only 50 millimeters from the edge. It's not quite at fully the edge. So we got to figure out tau at those 2 points. And then also sketch the shear stresses on the differential element at this point. So we'll actually just kind of sketch those in relationship to this picture. So that's what we're going to do. All right. So to get the shear stresses, we're going to use the torsion equation. Tau, right, the shear stress equals the internal reaction torque on the radius over J. We compute J. Rho is going to be 50 or 75 millimeters, depending on whether it's one point A or point B. And then T is the internal reaction. So again, I cannot state this enough. If you are going to find the shear stresses at point A, T is not 10 kilonewton meters. That is the external reaction torque. It's not necessarily equal to the internal reaction torque. In this case, it is not. Now, at point B, it just so happens that it is equal to this, the 4 kilonewton meters, but that's just because it's in per n. But T is not the external reaction torque. As always, this is one of those things I see constantly. I say it. I've said it already about 5 times in class. I still keep seeing it. But understand these equations. This is the internal reaction force. Whenever you're determining stresses, it's always in terms of the internal reaction forces. For simple loadings, often those are equal to the external ones, but not always. Okay? Please don't make that mistake. All right. We also need J. All right. So let's do J. Let's get that out of the way. Let's keep everything in terms of meter length units and also newtons for forces, and that would be pascals for stress. Okay, let's just keep it that way. And as you do more of these, you'll see that actually it's better to do like millimeters than pascals. But let's leave it this way for now. Now, actually, in the course of the way these lectures are shown, I haven't really derived this yet, but, well, I did derive this. We know that J, by definition, is the integral over the area of rho squared dA, right? That came about from the initial derivation. I'll have another video follow up to this where I talk a little more about J. But one that you really should memorize is for a solid rod, J is going to be pi over 32 times the outer diameter, d to the fourth. Now the fourth comes about from the fact that you've got area, so it's length squared, you have a rho squared side, so it's to the diameter to the fourth. So the units for J are going to be meters to the fourth power. So they're going to get really small because we have millimeters to the fourth, or even smaller than millimeters per second, which are even smaller than millimeters, right? So that's J. In this situation, outer diameter is 150 millimeters, or 0.15 meters, right? Use the radius. radius, double the radius, 150 millimeters. Well, we want it in terms of meters, so we swing the decimal points over a few spots. All right. So when we do that, we get I get J equal to 4.97 re-engineering digits times 10 to the minus fifth meters to the fourth. Okay, that's J. Right? And it's the same J for the whole length. It doesn't change. So that's J. All right, great. Now we need to get the internal reaction torque T. It's going to be different at point A than it is point B. So let's talk about that for a second. Okay, excuse me if I'm going a little slow in here, but this is the first problem solved. Try to go a little slow. The other subsequent problems are just quick speed. So this is the way the book draws the torques. They have little curvy arrows that go around. I'm not really a big fan of that. And I'll talk about this in class as well. But I prefer to draw it in a different manner. And actually, I like it because it makes everything seem axial. So let me draw this instead of this nice 3D sort of picture, because I have no way of drawing those. I'm going to draw the side view. So here's the fixed edge. That's what's called C. All right? Here's the rod. At this point here, the very end point, that's where we have the 4 kilonewton meter torque going in a counterclockwise manner around what's called this x-axis. Okay? Now, the way I prefer to draw it is using sort of right-handed thumb rule moment thing. So if you think about a right-handed torque, that means that the torque vector, or really the moment vector, is acting down the positive x-axis. It's acting like this. So I'm going to always draw these as follows, right? It looks like a vector, but I put 2 arrowheads on them because it's to differentiate a torque vector or a moment vector from a force vector. Well, really, a moment and a torque have the same thing, so the same way. We usually use torque around. I think that looks like a Shear, but it's really a moment. Now, at this point, this intermediary point, right, the torque is going the other way. So the right-handed sense is actually negative extraction. So actually, the torque at this other point is the torque vector going that way. So this is 10 kilonewton meter tech torque acting around the negative x direction, and this is the 4 kilonewton meter torque. Okay, acting around the positive x direction, positive x axis. I prefer that, and I'll show you why in a second. It makes everything look like axial. So I already put this. Here's the x direction, right? So here is the torque at the end. That's the 4 kilonewton meter acting about the x-axis. And then at the intermediary point here, it is more negative. So the other torque will apply. That's in the negative x direction. This is the 10 kilonewton meter force. Torque, I should say, right? Here is, in between here is point A on the side. That's point A. And up here, on the top, is point B. Okay? All right. Let's first do B. Okay? So, to get tau at B, right? We know that's going to be internal reaction torque at B times the radius over J. We already figured out J. In this case, picture here they show B at the outer surface, so the radius is the outer radius, the 0.75 millimeters. In this case, it is below 0.075 meters. Remember, it's the radius. This is the radius. Don't put the diameter on. We'll put that in the diameter. State. We've already figured out J is 4.97 to the minus fifth meters to the 4. You need to figure out the internal reaction torque through this plane, okay? Not the external. So let's draw the free body diagram. Make a cut there. Here's point B up on top. We've got to find the internal reaction torque at this base. Here is the 4 kilonewton meter. That's the external reaction torque. So that has to balance with the internal reaction torque. Here, this is actually the internal reaction torque at point B. And that has to be equal to 4 kilonewton meters. Actually, in this case, it is equal. All right? You can see actually if you take the double arrows and make them single arrow, force vector instead of torque vectors, it looks just like an axial problem. And again, at this point, it doesn't make a difference. But when we talk about statically indeterminate torsion problems, and when we talk about angular twist, just like in the axial problems, it will be important to get the correct orientation for the internal reaction torques. And it's a little confusing to think about which way they should go internally. At least for me it is. But when I do it this way, it follows the same convention as axial. The positive internal reaction torque is the one that goes in the outward normal direction. So that actually should be a positive internal reaction torque. I'm always going to draw the internal reaction torques in this direction. So the internal reaction torque at B is 4 kilonewton meters. So it just happens to equal the external one, but you know, it's not the external, it's the internal. So when we do this, this now becomes 4,000 newton meters times the radius, 0.075 meters over J, which is 4.97 to the minus fifth meters to the fourth. You can see the units here. I get newton, meters squared over meters to the fourth. So that's going to give me newtons per meter squared, or pascals. Let's do the numbers. And here I get 6.04 times 10 to the 6th pascals. 6.04. That's the shear stress of that. Okay. Now let's try to visualize that. Let me visualize it on the fancy picture 4. This would be where we would try to visualize it. So let's do it down here. So what's going on at this point? Let's kind of blow this point up. So here is a little differential element at that point. Okay. This is point B. This is the outer surface. Now, the shear stress at this point, think about it, it's going to want to take that face and it's going to want to shear it in this direction. Right? So in other words, these are two directions. That 4 kilonewton force is going this way. So with B on the top, that's the way it goes. So the shear plane is actually this plane here. So that means the shear stresses are acting on this face in that direction. You can see that's what's going on here. That torque, the shear on this front face going in that direction. Obviously another one in this other direction. But you can't just have those. They are always balanced out because if you just have these, then you lose the torque. So back face. Okay? That's the shear stress. This is B. This is the x-axis. Let's call this the y-axis. Let's call this the z-axis. So this would be tau in the x, z plane. It's going to equal 6.04. Okay? That's how it's visualized at point B. This is point B. Try to draw it in the same orientation as this picture. All right, let's do the same thing, but for point A. So let's go back and do point A. So this point. Now, we still have the same J, but in this case, point A is not at the outer radius, it's at 0.05 meters, or 50 millimeters. So rho is going to be 0.05, and the internal reaction torque is going to be different, right? So we have to take this cross section here, so this cross section here, do that. Okay. This is going to expose that face. Here is the internal reaction torque I want to find. Internal reaction torque at point A. I drew it in this direction. So on that face, that's the positive orientation, just like an axial, outward normal. Now what balances that? Here are the external torques, 4 kilonewton meters. Here is 10 kilonewton meters. All right, so this is another point where I think drawing it this way kind of makes life easier, because this just goes the same way as axial. For some reason, torque gets a little more confusing, but when we do the axial stuff, right, you just step back and let these double arrows become single arrows. It's quite easy. From here, you can see sum of forces, really sum of moments about the x-axis has to equal 0. So that's going to be minus torque A, minus x direction, minus the 10 kilonewton meters plus 4 kilonewton meters has to equal 0. Or in other words, internal reaction torque at A equals minus 6 kilonewton meters. So it's actually torquing around the other way. It's actually on this face, it's actually going to torque this way, so it's actually going to go that way, right? The shear force directing that way, right? Into the board, okay? Into the page. That's what it is. But you can see how easy it is to figure out here. This were axial, it's quite obvious that these two sum up and equal that. So this one has to be actually 6 in the other direction with 4 to balance the 10, right? So I think it makes it easier to visualize it this way. But, if you like drawing them like this with the little goofy things, that's fine. All right, so there's my internal reaction torque. All right, you can see it's not 4 and it's not 10, right? It's different, right? It's internal. It's not one of the externals. It's actually the same as the reaction. Okay, so now the shear stress at point A is that internal reaction torque, minus 6,000 newton meters. For the shear stresses, you don't have to worry so much about the sign, but I'll keep it in there because when we do angular twist and whatnot, it's looking at. So 6,000 newton meters. The radial distance here is the 0.05 meters, right? It's not at the outer limits, it's 3/4 meter. And then J is the same. The diameter of the geometry at point A is the same as geometry at point B. So J is still 4.97, so minus fifth meters to the fourth. This will give me this gives me almost the same stress. This gives me 6. Well, actually, if I take it out to the same number of square difference digits, I actually get the same exact stress. Okay, so you get the same stress, even though the internal reaction torque is more, but that's because you're not at the outer radius. The maximum shear stress you would find here, A, really at the outer radius, would be the minus 6,000 newton meters times the 0.075 meters over 4.97 e to the minus 5 meters per fourth, or actually another 25% on top of this. 7.56. That would be the shear stress at the same cross section as A, but at the outer radius. Okay? All right. So now let's visualize it. But actually, the problem really is asking. That's the answer. All right. So now let's do the visualization. Okay? So let's go back to this picture. I know what the value should be. The value should be, the same 6.04 megapascals. But at this point, we have to draw it. So let's draw the little differential element that sits here. Okay? So let's draw that over here. Try to draw these parallel to X. This is going in the radial direction. Okay? This is at point A. Right? Now, how is this going? Well, the plane that this is going to act on is obviously has to be, let me do a pencil, it's going to be on this plane, right? It's going to be on this plane, right? Now the question is, on this face, is the shear force acting down or is it acting up? Okay? On this front face, acting down or is it acting up? Well, let's think about it. Let's see if we can kind of visualize it. Let's go back to this picture, right? So, what's going on here? Well, draw this segment, actually, if you draw this little widgety guy, let's say it sits here, okay? Here's our little differential element. Okay? So on this face, the torque is going that way. On this face, the torque, right? Because I got negative things, right? So it's actually going. So if that's the case, if it's actually going, this is the back face of the cube, right? It's actually going this way. That means the torque on the back face is acting up. Up. Right? It's acting up. Keep my right hand. Up. And the torque on the front face is also going in, right? In on this front face. And so when it comes around point A, it's acting again. Does that make sense? Right? So on this face, it should actually act down. And on this back face, it's going to be acting up. That makes sense. Like again, if you draw the back face, do the torque. These are my left hand. Sorry. That's fine. I'm using my left hand. I'm using my right hand. Sorry, let's go back. Sad. Let's go over that again. Okay. All right. So obviously it's acting in this point. It's going to be acting in y x plane. Right? Y x plane. Which direction is that in this case? So let's go back, basically look at a little differential element here, right? So let's see if we can go this way. Here's the little differential here. Here is A, right? Here's that differential here, okay? We're at this sort of 9 o'clock position. All right. Now, what am I saying? When I drew this, right, when I drew this free body diagram, this is the back face of that. Torque is actually, my right-handed rule. It's going in, so it's going on that, right? So when it gets around at 9 o'clock, the shear stress force is acting down in the direction of my fingers. Okay? So that means on this back face, it should be acting down. That's the cut face, right? That's the cut face. Back. So that means that this front face is actually acting down. Okay? Right? And then obviously that's balanced. So actually the shear stress in this picture is as follows. Up, this way, back this way. The value, this is tau, it's acting in the y x plane. So it's an xy shear stress. And it's equal to the 6.04 megapascals. Okay? So that's the way it looks like. All right? So it's actually flip direction. All right. Try to think about that. This is a little confusing in direction, but actually when we start to talk about statically indeterminate ones, it's going to be nice if you have a little better feel for it. Okay? But I know it's totally obvious right from the start. Okay? I think though if you do get used to this, it does work out. All right.